The destruction of an 85,000-pound, four-engine bomber can be traced to a small, unsecured gas can used as a temporary fuel supply. In the complex mechanical hierarchy of aviation recovery, the largest components often receive the most focused engineering attention. Teams calculate wing spar loads, engine compression ratios, and runway bearing strengths with precise discipline. Yet the failure that dismantles the operation frequently originates in a temporary, improvised connection that bypasses the primary design. For the Boeing B-29 Superfortress, known as the Kee Bird, the chain of events that converted a preserved artifact into a charred wreck did not begin with a structural collapse or a pilot error. It began with a jury-rigged fuel supply for the auxiliary power unit, an improvised can and hose setup intended as a temporary workaround. This specific mechanical choice demonstrates the unforgiving nature of field restoration, where a single deviation from standard procedure can negate months of logistical success. The aircraft itself was a relic of the early Cold War, a late-war B-29 that had been modified with camera installations for long-range photographic reconnaissance, often described as an F-13 photo recon Superfortress. In 1947, it had settled onto the surface of a frozen lake in northwest Greenland. For 47 years, the airframe remained on the ice, located at 80 degrees north latitude. The high Arctic environment acts as a sterile preservative for aluminum and steel. The dry, freezing air halts the electrochemical processes of corrosion that typically consume wreckage in warmer or wetter climates. When the recovery team arrived in 1994, they did not find a rusted hulk. They found a time capsule, structurally intact and waiting for energy to return to its systems. The objective of the 1995 expedition was absolute and binary. The team intended to repair the aircraft on the frozen lake surface and fly it out to Thule Air Base. This was not a dismantle and transport operation. The logistics of the site effectively removed the option of heavy lift extraction. No helicopter capable of lifting a B-29 fuselage possessed the range to reach the site and return with the load. Disassembly would have required cutting the main spars, permanently destroying the historic integrity of the airframe. The engineering solution was to bring the factory to the ice. The plan required replacing 4 massive radial engines, fitting new propellers, and hanging new flight control surfaces in an open-air environment exposed to polar winds. This approach relies on the principle of competence under constraint. The engineers had to replicate the functionality of a heavy maintenance hangar without the infrastructure of a roof, power grid, or pneumatic supply. Every tool, bolt, and gallon of fluid had to be flown in by a support aircraft landing on a rough strip graded into the mud and ice. The margin for error in such an environment is non-existent. A missing gasket or a stripped fastener cannot be replaced by a run to a supply depot. The team must work with exactly what they have transported to the site. In this context, ingenuity becomes a required resource. Engineers effectively trade safety margins for operational feasibility. They fabricate brackets, reuse clamps, and bypass non-critical systems to focus effort on the primary flight controls. However, complex machines like the B-29 do not tolerate improvisation in their energy systems. The concept of the single point of failure is central to understanding why this recovery ended in loss. In a redundant system, a failure in one channel is absorbed by a backup. A B-29 has 4 engines, dual magnetos, and multiple radio sets. But during a field restoration, the temporary support equipment often lacks this redundancy. If a ground power unit fails or a heater line freezes, the operation halts. If a temporary fuel line fails, the consequences can cascade immediately into a thermal event. The engineering discipline required to manage these temporary systems must be as rigorous as the discipline applied to the flight surfaces. When that discipline relaxes to solve a minor problem quickly, the risk profile of the entire project shifts. The Kee Bird sat on a frozen lake that provided a runway of infinite length but limited duration. The operation was bounded by the seasons. The spring thaw would weaken the ice, turning the runway into slush and then open water. The team worked against a hard deadline defined by the solar cycle. This pressure creates a decision-making tunnel where the immediate goal of starting engines can overshadow the procedural safety checks that would be mandatory at a home base. The focus narrows to the rotating machinery. The engines must turn, the propellers must govern, the controls must move. In this intense focus on the major systems, the peripheral support equipment, like the small auxiliary power unit located in the rear fuselage, can be perceived as a trivial utility rather than a hazard. The loss of the Kee Bird provides a documented case study in the physics of unintended consequences. The aircraft had survived a forced landing in 1947 with comparatively minor airframe damage for a forced landing and no serious injuries to the crew. It had survived nearly half a century of blizzards and ice movement. It was destroyed not by the elements but by the thermal release of its own fuel during the final moments of the recovery effort. The transition from a priceless restoration project to a total hull loss occurred in minutes. It demonstrated that in aviation archaeology, the most dangerous phase is not the decades of abandonment, but the brief window of reactivation. When energy is reintroduced to a dormant system, the dormant risks wake up. The investigation into this failure does not require speculation about curses or bad luck. The evidence trail is physical and clear. It involves the geometry of a fuel can, the placement of an exhaust pipe, and the vibration of an airframe coming alive after 47 years of stillness. By examining the mechanical decisions that led to the fire, we can understand the precise trade-offs made by the team. They achieved the impossible task of reviving the engines, only to lose the prize to a hazard that was manageable, predictable, and ultimately fatal to the airframe. The story of the Kee Bird is a ledger of technical brilliance balanced against a single, catastrophic procedural bypass. The first time the Kee Bird touched the ice came at the end of a mission that launched on February 20th, 1947, and ended with an emergency landing on February 21st. The aircraft belonged to the 46th Reconnaissance Squadron. Its mission was part of Project 8, a strategic initiative to map the polar regions and test long-range navigation limits. The crew found themselves disoriented over the high Arctic after their solar compass lost its reference. Without a reliable heading and with fuel tanks registering near empty, the pilot, Lieutenant Vern Arnett, faced a binary decision. He could order a bailout into the dark tundra, scattering the crew across miles of lethal terrain, or he could attempt a controlled wheels-up landing on the frozen surface of an unnamed lake. The physics of a forced landing on ice differ significantly from a ditching in water. Water exerts a hydrodynamic drag that tears airframes apart instantly upon contact. Ice, covered by a layer of hard-packed snow, acts as a friction brake. When the Kee Bird contacted the surface, it carried the kinetic energy of a 60-ton mass moving at over 100 miles per hour. The pilots kept the landing gear retracted to prevent the struts from digging in and cartwheeling the fuselage. The smooth aluminum belly of the B-29 acted as a sled. The aircraft slid across the snow, dissipating energy through friction until it came to a rest. The structural integrity of the fuselage remained 100% intact. No spars were bent, no fuel tanks ruptured. The propeller tips curled back as they struck the ice, but the engines themselves remained mounted on the wings. This successful energy management resulted in the survival of the entire crew. They were eventually evacuated by a C-54 Skymaster and flown to the Thule Station area, leaving the bomber behind. For the next 47 years, the Kee Bird sat on the lake surface, subjected to an environmental test that few machines ever endure. The Arctic climate is often described as hostile, but for aluminum structures, it is a near-perfect preservation chamber. The extremely low humidity and consistent sub-zero temperatures inhibit the chemical reactions that cause corrosion. In a jungle or coastal environment, oxidation and galvanic corrosion would reduce a B-29 to a skeleton within 2 decades. On the Greenland ice sheet, the metal skin retained its polish, the control cables remained tensioned, the glass in the cockpit remained unbroken. However, this visual preservation creates a dangerous engineering illusion. While the metal survives, the environment aggressively attacks the soft goods of the aircraft. Rubber seals, gaskets, hoses, and electrical insulation lose their elasticity in the extreme cold. They become brittle and crack under the slightest manipulation. This phenomenon is compounded by the concept of thermal shock and cold soaking. When a complex assembly like a radial engine sits at temperatures fluctuating between -20 and -60 degrees Fahrenheit for nearly half a century, the different metals within the engine, steel liners, aluminum pistons, magnesium cases, contract at different rates. This differential contraction creates stress risers within the engine block. A bolt that was torqued to specification in 1947 may have loosened or snapped solely due to thermal cycling. Lubricants turn into solids that resemble wax or glue. When a recovery team attempts to rotate a cold-soaked crankshaft, they risk scoring the cylinder walls or shattering brittle piston rings. The environment essentially fuses the moving parts into a single solid block. To return the machine to operation, the team cannot simply add fuel and turn the key. They must apply heat slowly and methodically to reverse the contraction before applying any mechanical load. The location of the Kee Bird introduced a logistical paradox that defined the entire 1995 operation. The lake was accessible enough to land a small support aircraft, but it was too remote to support a ground-based extraction. The site lay hundreds of miles from the nearest deep water port or heavy-duty runway. There were no roads. The terrain between the coast and the lake consisted of glacial ridges and soft tundra that would swallow a heavy transport vehicle. This geography imposed a harsh filter on the recovery options. The team could not dismantle the aircraft and truck it out. They could not lift it out with existing helicopter technology. The only path that satisfied the physics of mass and distance was for the aircraft to fly itself out. This reality locked the team into a restoration-at-site methodology. In a standard museum recovery, the goal is to stabilize the wreck and move it to a controlled facility where work can proceed over years. On the ice, the restoration has to happen in the wild. The hangar is the open sky. The workbench is the frozen lake. The timeline is dictated by the sun. The team had to perform heavy maintenance, work that usually requires overhead cranes and hydraulic lifts, using only what they could fly in on a small shuttle plane. The trap of the Kee Bird was its apparent readiness. It looked like a flyable airplane parked on a runway. This visual feedback suggested that the machine was ready to serve, masking the reality that every seal was compromised and every lubricated surface was dry. The environment had saved the structure but destroyed the internal nervous system of the aircraft. The challenge was not aerodynamic, it was chemical and mechanical. The team had to replace the heart of the aircraft, the four engines, while standing on a surface that was slowly melting beneath their boots. The decision to fly was not made out of recklessness, it was the only mathematical solution that solved the equation of weight, distance, and available lift. But it required the team to place absolute trust in their ability to reverse 47 years of thermal entropy in a matter of weeks. The recovery plan for the Kee Bird was determined by a rigid calculation of range versus payload. The engineers faced two distinct options. They could cut the bomber into sections to facilitate a helicopter extraction, or they could restore the aircraft systems and fly it out under its own power. In a standard recovery closer to civilization, the section lift is the preferred method. It minimizes risk to human life and guarantees the retrieval of the artifact, albeit in pieces. However, at 80 degrees north latitude, the section lift was mathematically impossible with the available hardware. Heavy lift helicopters, such as the Sky Crane or the Chinook, lack the ferry range to reach the site, lift a fuselage section weighing tens of tons, and return to a base with fuel in reserve. The geography of Greenland effectively removed the option of external lift. The aircraft had to fly, or it would remain on the ice. This binary constraint shifted the operational focus to logistics. If the B-29 was to fly, it required a runway. If it required a runway, the team needed heavy earth-moving equipment to grade the ice. If they needed earth-moving equipment, they needed a transport aircraft capable of delivering it. The entire project hinged on a 1962 de Havilland Caribou, a twin-engine tactical transport designed for short takeoff and landing operations. This aircraft became the lifeline for the expedition, acting as the only bridge between the industrialized world and the frozen lake. The logistical challenge is best illustrated by the transport of the runway construction equipment. The team required a bulldozer to clear the snow and grade a 4,000-foot strip on the lake surface. A standard case 450 bulldozer exceeds the payload and dimensional limits of a Caribou cargo hold. To solve this, the engineers applied a radical form of field modification. They used cutting torches to slice the bulldozer into manageable subassemblies, separating the blade, the tracks, and the frame. These components were loaded individually into the Caribou, flown to the ice, and then re-welded and reassembled on site. This process defines the concept of field restoration logistics. The team could not simply order a resource. They had to fabricate the capacity to use that resource within the strict weight limits of the delivery vehicle. The Caribou flights themselves operated at the edge of the performance envelope. The landing zone was not the frozen lake itself, but a mud flat on the shoreline that offered a temporary friction surface during the summer months. The approach required precise energy management. On one specific rotation, the Caribou experienced a mechanical failure of its flap system. The flaps provide the necessary lift and drag to fly at slow speeds for landing. Without them, the pilot was forced to execute a high-speed approach onto the soft terrain. The aircraft touched down well above standard landing speed, careening across the mud and narrowly avoiding a catastrophic overrun. This incident underscored the fragility of the supply chain. If the Caribou was lost, the team would be stranded, and the Kee Bird project would end immediately. Despite these hazards, the logistics machine delivered the necessary components. The reassembled bulldozer successfully graded a 4,000-foot runway on the ice. This strip was smoothed to a tolerance that would allow the B-29 to accelerate to takeoff speed without shattering its landing gear. With the infrastructure in place, the team turned their attention to the bomber itself. The assessment of the airframe confirmed the initial hypothesis. The structure was sound. The spars were straight. The skin was uncorroded. The control cables, while old, moved freely through their pulleys. The identity of the aircraft was never in question, but its integrity as a flying machine had to be proven component by component. The critical decision was made to replace the motive power entirely. The original Wright R3350 engines were notorious for overheating and carburetor fires even when new. Attempting to run engines that had sat for 47 years was deemed an unacceptable risk. The team sourced 4 zero-time engines, essentially brand new old stock, and 4 propeller assemblies. These were not direct replacements. They were remanufactured Wright R3350 engines and matching propeller assemblies integrated into a vintage airframe under field conditions. This choice was a deliberate engineering trade-off. The fuel injection system reduced the risk of induction fires, a common failure mode for the B-29. However, it introduced a new variable: the installation of modern distinct systems into a vintage airframe in sub-zero conditions. The process of hanging 4 engines on a frozen lake is a study in physical endurance. Each engine weighs nearly 3,000 pounds. The team constructed a gantry system on the ice to hoist the power plants up to the wings. This was done without hydraulic lifts or precise positioning tables. It was done with chain hoists, muscle, and verbal coordination. The wind chill often dropped the effective temperature to -20 degrees or lower. In these conditions, metal tools freeze to expose skin instantly. The mechanics worked in shifts, warming their hands on portable heaters before returning to the torque wrenches. By late 1994, the physical presence of the Kee Bird had changed. It was no longer a derelict. It sat on fresh tires, its tires inflated for the first time in decades. It had 4 new engines installed. A smooth white runway stretched out in front of its nose. The team had successfully transported the capabilities of a heavy maintenance depot to the top of the world. They had proven that the logistics could support the engineering. The aircraft was theoretically capable of flight. But as the winter darkness closed in, forcing the team to depart until the following spring, the project shifted from a structural challenge to a systems challenge. They had built the skeleton and the muscles. In the coming season, they would have to wake up the nervous system. The restoration of the Kee Bird was bounded by a strict environmental deadline defined by the solar cycle. In the high Arctic, the transition from winter to spring is not merely a change in temperature, it is a structural degradation of the operating surface. The lake ice, which provided a concrete-like foundation during the dark months, begins to lose its bearing strength as the sun rises higher. The top layer softens into slush, increasing rolling resistance for aircraft wheels. Beneath the surface, the ice sheet undergoes thermal expansion, creating pressure ridges and cracks that can swallow a landing gear strut. The team had to complete the complex integration of 4 power plants and flight control systems before the runway lost its integrity. This time, window created a pressure curve that steepened with every degree of solar elevation. The physical interaction with the B-29 required a procedure known as in situ stabilization. Before the engines could be tuned or the controls rigged, the airframe had to be lifted from its resting position. The aircraft had settled onto its tires in 1947, and over the decades, the weight of the fuselage had pressed the flattened rubber into the ice. To free the machine, the team utilized hydraulic bottle jacks placed under the main gear trunnions. This is a standard hangar procedure, but on a frozen lake, it introduces a dangerous variable. The base of the jack does not rest on a verified concrete floor. It rests on ice that may shift or crack under point loading. The engineers had to distribute the load using timber cribbing to prevent the jacks from punching through the surface and dropping the 100,000-pound airframe. Once the aircraft was elevated, the team addressed the rolling stock. The original tires, 56 inches in diameter, were frozen into distorted shapes. While the rubber had not rotted due to the preservation effects of the cold, it had taken a permanent set. The team removed the wheels, massive assemblies of magnesium and rubber, and replaced the tires with fresh units flown in by the Caribou. This step was critical. A blowout during the takeoff roll on a rough ice strip would not just abort the mission, it would likely result in a loss of directional control and a catastrophic breakup of the airframe. The installation of new tires effectively converted the Kee Bird from a static monument back into a mobile vehicle capable of interacting with the runway. However, the most severe constraint in this phase was not mechanical, but biological. The remoteness of the site meant that the expedition operated beyond the safety net of modern medicine. In an industrial setting, a medical emergency is resolved by a 10-minute ambulance ride. At 80 degrees north, the distance to care is measured in flight hours and weather windows. This reality materialized when the project's chief engineer, Rick Krieg, fell ill. Krieg was the technical architect of the engine replacement and a central figure in the mechanical logic of the recovery. His symptoms initially appeared to be minor, attributed to the strain of working 18-hour days in sub-zero temperatures. The situation deteriorated rapidly, revealing the unforgiving nature of the medical risk in remote zones concept. When a crew member becomes incapacitated in a deep field environment, the logistics chain must reverse direction immediately. The priority shifts from importing parts to exporting the patient. However, the Arctic weather operates independently of human urgency. A storm system grounded the support aircraft, forcing the team to manage a critical medical situation in a tent on the ice. The delay in evacuation extended for days. By the time the weather cleared and Krieger could be flown to a hospital in Canada, his condition had advanced past the point of intervention. He died 2 weeks later from a blood clot. The loss of the chief engineer imposed a heavy psychological and operational tax on the remaining crew. In a standard engineering project, the loss of a lead can be mitigated by bringing in a replacement. On the ice, Krieger's knowledge of the specific idiosyncrasies of the Kee Bird systems was irreplaceable. The team had to press forward, driven now by a somber obligation to finish the work he had started. The death removed the sense of adventure that often characterizes vintage aviation recovery. It reframed the operation as a harsh industrial job that had already claimed a life. The margin for error, already slim, was now shadowed by the reality that the environment was lethal. Despite this setback, the mechanical work reached its conclusion. The 4 new R3350 engines were bolted to the firewalls. The propellers were timed, the control surfaces were rigged and tensioned. The aircraft sat high on its new tires, separated from the ice that had held it for 47 years. The team had successfully transformed a wreck into a functioning machine, at least statically. But the final validation required dynamic energy. The systems had to be tested under load. As the spring melt accelerated, turning the runway edges into water, the team prepared to wake the machine. They had won the battle of statics and assembly, but the battle of thermodynamics and fluid flow was about to begin. The Kee Bird was ready to move, but the cost of reaching this point had already exceeded the worst-case estimates. On May 21, 1995, the restoration of the Kee Bird transitioned from a static repair operation to a dynamic flight test. The 4 newly installed radial engines were started, settling into a steady idle that resonated across the frozen lake. For the first time in 47 years, the airframe was vibrating with internal energy. The extensive checklist of the previous months, the engine changes, the control rigging, the tire replacements, had all been marked complete. The runway stretched out for 4,000 feet, graded and smoothed. The weather window was open. The objective of flying the aircraft to Thule Air Base appeared to be a matter of executing a standard taxi and takeoff sequence. However, within the complex systems of the B-29, a single improvised decision was about to interact with the laws of thermodynamics to force a catastrophic trade-off. The pivot point of this failure centered on a secondary system located in the rear fuselage, the auxiliary power unit. In the design architecture of the B-29, the main engine's drive generators that supply the 28-volt direct current required for the aircraft's electrical bus. However, at low engine speeds or during ground operations, these main generators may not provide sufficient stable current. To bridge this gap, the aircraft is equipped with a small, two-cylinder gasoline engine driving an independent generator. This unit, often referred to by crews as the putt-putt, provides the electrical power necessary to operate lights, radios, and critical instrument motors when the main power plants are idling. The restoration team faced a specific constraint regarding this unit. The original fuel lines running from the main tanks to the auxiliary power unit were buried deep within the fuselage structure. After decades of cold soaking, the integrity of these lines was suspect. To avoid the risk of a hidden leak or a blockage from old varnish, the engineers elected to bypass the airframe's fuel plumbing entirely. They constructed an improvised fuel system. This consisted of a simple external tank, roughly the size of a standard 3-gallon jerry can, suspended from the fuselage structure above the auxiliary power unit. A rubber hose ran from this can directly to the unit's carburetor, feeding fuel by gravity rather than by pump. This solution is a common workaround in field mechanics for testing engines on a bench. It isolates the engine from the vehicle's fuel system constraints. However, applying this bench test logic to a moving airframe introduced a critical flaw. The B-29 is not a static bench. When 4 R-3350 radial engines are running, they generate a specific vibration spectrum that transmits through the entire aluminum structure. As the aircraft began to taxi, the fuselage acted as a resonator. The improvised tank, suspended by wire or straps rather than a rigid, certified mounting bracket, was subjected to these oscillations. The physics of the failure were dictated by geometry. The improvised tank was positioned directly above the auxiliary power unit. The unit's exhaust stack, which reaches temperatures sufficient to ignite hydrocarbons instantly, was located directly below the fuel source. In a certified aviation fuel system, rigid lines and pressure fittings prevent leaks even under high vibration. In the improvised gravity feed setup, the connection between the hose and the can relied on a simple friction fit, or a basic clamp. As the aircraft taxied over the uneven ice of the runway, the vibration and the physical jostling of the fuselage compromised this connection. Fuel began to leak from the container. It did not drip into a containment tray or drain overboard. It followed the path of gravity directly onto the hot exhaust casing of the running generator. The ignition was immediate. Because the auxiliary power unit is located in the rear, unpressurized section of the fuselage, far behind the pressurized crew compartment in the nose, the fire established a thermal foothold before the crew was aware of the ignition. The noise of the 4 main engines masked the sound of the small generator struggling or the initial crackle of the fire. This moment represents the decisive pivot in the operation. The engineering team had successfully managed the macro constraints of the project. They had solved the heavy lift logistics, the engine replacement, and the runway construction. Yet the outcome was being determined by a micro component that had been treated as a utility rather than a hazard. The decision to use a gravity feed tank was a trade-off between the time required to restore the original hardlines and the expediency of a quick fix. In a controlled environment, a fuel spill from a 3-gallon tank might be managed with a fire extinguisher. In the confined, highly flammable interior of an aircraft tail section fed by a continuous stream of gravity-driven fuel, it created a self-sustaining firestorm. The fire rapidly consumed the combustible materials in the rear section: insulation, hydraulic fluid, and magnesium components. By the time the smoke became visible to the ground crew and the pilots, the damage capability of the fire exceeded the suppression capability of the handheld extinguishers available on board. The operational logic shifted instantly from recovery to survival. The goal was no longer to fly the aircraft out. The goal was to stop the taxi and evacuate the fuselage before the fire compromised the wing tanks. The logic of the improvised system had overridden the logic of the restoration. The Kee Bird was no longer a restored bomber. It was a structure rapidly losing its integrity to an internal energy release that could not be stopped. Fire within a confined aluminum structure creates a thermal runaway condition that no handheld extinguisher can suppress. Once the combustion of fuel heats the surrounding metal, The fuselage itself acts as an oven, reflecting radiant energy back into the core of the fire. On the ice of Greenland, the crew of the Kee Bird faced this precise thermodynamic scenario. The fire that began at the auxiliary power unit did not stay contained to the generator. It immediately ignited the doping compounds on the fabric control surfaces and the hydraulic fluid residues in the tail section. The operational status of the aircraft shifted instantly from a taxi test to a hull loss event. The reaction of the flight crew was dictated by the lack of sensors. The B-29 design does not include fire warning loops in the rear unpressurized section for the auxiliary power unit. The pilots in the forward cockpit were physically separated from the fire by a 60-foot pressurized tunnel. They were alerted not by an instrument light, but by the frantic visual signals of the ground crew outside the aircraft. As the smoke began to pour from the rear gunner's station, the pilots cut the mixtures to the 4 main engines. The propellers, which had been pulling the aircraft forward, slowly wound down to a halt. This action stopped the airflow over the fuselage, but it also removed the vibration that had started the leak. By then, the fuel saturation was sufficient to sustain the burn. The evacuation of the aircraft was disciplined but urgent. The crew exited through the forward hatches onto the ice. Cook and mechanic Bob Vanderveen suffered minor smoke inhalation and burns, representing the only immediate physical injuries during the fire. However, the aircraft itself was entering a terminal structural failure mode. Aluminum alloys used in aviation construction maintain their strength only within a specific thermal envelope. As the temperature in the tail section exceeded 400 degrees Fahrenheit, the metal lost its rigidity long before it actually melted. The longerons, the longitudinal beams that provide the fuselage with its stiffness, buckled under the heat load. The consequences of the fire severed the mechanical continuity of the airframe. The control cables for the elevators and rudder, which ran through the roof of the fuselage, snapped as the structure warped. This was the definitive end of the aircraft as a controllable machine. Within minutes, the aft fuselage was heavily compromised by fire, and the aircraft's structure was rapidly rendered unrecoverable. The fire then migrated forward, fed by the prevailing wind and the combustible materials inside the camera bays and crew stations. The team could only stand on the runway they had built and watch the destruction of the asset they had spent a year restoring. The heat of the fire introduced a secondary destruction mechanism, the phase change of the runway itself. The frozen concrete that had supported the 100,000-pound bomber turned back into liquid water. As the fire intensified, it melted a depression into the lake surface. The Kee Bird did not just burn, it sank. The fuselage settled into the slush, effectively extinguishing the lower fires, but ensuring that the wreckage would be frozen into the lake bed when the winter returned. The 4 brand-new engines and propellers, which had run for less than an hour, were dragged down with the wings. Today, the site remains a testament to the harsh limits of field engineering. The wreckage of the Kee Bird sits in the shallow water, partially visible depending on the season and ice cover. It is no longer a preservation target. It is an archaeological site of a failed recovery. The 18 months of logistical success, the caribou flights, the bulldozer reassembly, the engine changes, were negated by the failure of a single, non-redundant component. The concept of the single point of failure remains the defining lesson of the expedition. A restoration effort is a chain of thousands of links, ranging from massive wing spars to 3-gallon plastic tanks. The strength of the recovery is determined not by the strongest link, like the new engines, but by the weakest link, the improvised fuel feed. The legacy of the Kee Bird project is not the hardware that was lost, but the data it provided to the aviation recovery community. It demonstrated the extreme risk of attempting to fly a complex, multi-engine aircraft out of a deep field site after decades of dormancy. It validated the alternative approach of cut and lift, where the aircraft is disassembled into helicopter transportable sections. While disassembly destroys the structural continuity, it guarantees the survival of the components. The fly-out method preserves the structure only if it succeeds completely. If it fails, the loss is total. The decision to attempt a fly-out was driven by the constraint of remote logistics and the desire to save the airframe in its entirety. It was a calculated risk that solved the weight and distance equation but failed the probability test of mechanical reliability. The Kee Bird remains at 80 degrees north, not as a museum piece, but as a permanent marker of the boundary between static preservation and dynamic operation. The ice, which had preserved the bomber for 47 years, reclaimed it in the end, aided by the thermal energy brought by the very team that tried to save it.